Okay, we are then sort of moving on to the next session, which is related to open resource educational materials and links to research on learning and on engineering education. And because we have all 6 presenters here, I will be very strict on time. So I will sort of give a sign after 8 minutes, and then you have 2 minutes to wrap it up. So 10 minutes sharp. But I know that for Germanic countries, it's possible, usually.
My name is Fellin, and I'm happy to present my talk about open educational resources for geotechnical engineering education. So now imagine you want to develop a new lecture or you want to update an existing one. First, you will think about the content of this lecture. Then you will think about how to visualize the things with pictures, figures, or videos. And maybe you'll think about material for additional exercises for the students. So then you have to decide if you want to produce the material yourself so that it fits perfectly to your purpose, and then the question arises, do you have time for that? And usually you're going to start searching in textbooks or search on internet, and as soon as you do this, you will encounter copyright issues. The problem with copyright is that it is not universally consistent across countries. And I'm pretty sure that most of you here do not believe a common misconception, that is, it's on the internet, so it's free to use. So actually, if there is no clear statement of the right of use, do not use the material. However, if you find an open educational resource, your life is going to be easy. What are open educational resources? These are learning, teaching, and research materials in any format and medium. They are public domain or have an open license, so there is a no-cost access to the material. You can reuse it, you can adapt it, and you can redistribute the material. So what is an open license? One versions are the Creative Commons licenses. They are well defined and established. They are perfectly suited for text, pictures, photos, videos, and similar material. However, if you want to publish software, you should use other licenses like the GNU General Public License. You can use CC0, which is called public domain. There you give up any right as a creator. I only recommend this for small materials like pictograms or small drawings. You could use CC BY, where the credit must be given to you as a creator. It does not work anymore. By the way, the phrase by is originated simply by created by. This material is created by, so this is called CC BY. There are no further restrictions to the material, so it is free to use. And handling CC BY is somewhere very similar to what we are used when we cite papers. So I highly recommend this when you produce open educational resource materials. Usually, creators from universities tend to use CC BY NC to prevent commercial usage. So due to BY, the credit must be given to you as a creator, and the NC should permit non-commercial usage. But the definition is somewhat imprecise, as it states not primarily intended for monetary compensation. And this imprecise definition makes the question if the usage is commercial or not somehow tricky, so that some people state this can only be answered in court. So it is possible to use CC BY NC for open educational resource, but I do not recommend it. You can try to use the attribute share-alike instead. The share-alike means that the adapted material must be published as share-alike again. So the commercial usage is difficult, not totally restricted, but very difficult. So this is a better alternative. So I recommend this for open educational resources. However, if possible, use CC BY. Now let's switch to some examples of open educational resources. Let's start with videos. What are the advantages of videos? Now, for example, you can include physical experiments to visualize important content. For example, you see here a sand dune, and you can increase the inclination better, and you can ask in advance at what angle better the sand will start to slide. Then you can show the experiment, and you can highlight then 2 angles. The one at which the sand starts to slide, and the other at which the deposit is formed. And these two angles can help you to explain critical soil concepts, critical state soil concepts like the peak friction and the critical state friction angle. So if you want to explain critical state and peak shear strength and the relation to the void ratio, in a textbook, you will end up with a pretty complex figure and a lot of text around it. The advantage of a video is that you can do this, that you can show the creation of such a figure step by step, just like you would do it on the blackboard. And you see here the evolution of the stress during the displacement, the evolution of the void ratio during displacement, the evolution of the void ratio during the critical void ratio. And you see here then the construction of the failure point in the normal stress shear stress diagram. You can repeat this with a sample with a lower stress level. You can highlight where the action goes, and then you will end up with the construction of a second point, and then you can construct a straight line, which is the shear stress line of the critical state, which is inclined by the critical friction angle. And the advantage of the video is now that the students can watch this video, or parts of it, as often as they want, and this is not so easy to implement in a traditional lecture. Another advantage of the videos is that you can enhance the didactic value of the video when you make them interactive. So for this you can use a format which is called H5P and an editor which is called Lumi. And with that you can interrupt the video with questions to activate viewers and repeat crucial content. For example, we stop here before showing the evolution of the void ratio towards the critical one, and then ask if the initial void ratio was higher or lower than the critical one, if the void ratio decreases or increases during shearing, and if the shear stress reaches a peak or not during shearing. And only if all three answers are answered correct, the viewers can continue watching the video. The last example I want to show are interactive worksheets. They are produced with a software called R exams, and these are HTML based, so they can run outside any learning management system. For example, you see here the theoretical part of such a worksheet where it is explained very simple how the vertical stress in a uniaxial unconfined compression test has to be computed. Students are given then this example for a given force and a given geometry. They should compute this stress. They can put in then their number there. They can check for the answer. Oh, this was wrong. They can try it again. And now they get the right answer, and they also can display the long version of the solution. So finally, some concluding remarks. So I think open educational material can be a great support for teaching, and they should have an open license. I recommend to use CC BY as an open license and to avoid CC BY NC. In addition, you have to ensure long-term availability for that material. For example, you can upload this to OER repositories. And although videos are a lot of works, they are very valuable for teaching. But you have to provide additional transcripts, as some people rather like to read than to hear. And if you have videos produced by another person, and this have an open license, it's easy for you and very quick to make this interactive and enhance the didactic value of this. And the last example I showed were interactive worksheets. They are produced with R exams, can run outside the learning management system, and are therefore open educational resources. And all of this material certainly must be included in the teaching concept, for example, flipped teaching, to be really effective. So if you want to have some examples, you can go to the Open Educational Resources repository of the University of Innsbruck. The link is given here and in the paper, and there's a collection called Soil Mechanics English, and you find the videos, the interactive videos, and some pre-versions of the interactive worksheets there. So that's all I wanted to say. Thank you for your attention.
Thank you very much for sticking to the schedule. So now it's time for questions or comments by the audience. well, my comment is that the reason I never share my teaching materials is that basically that I know that I'm continuous copyright violator because everything is done in a midnight oil and you don't even remember where you took things from. So I think that is one of the problems, and maybe sort of this Marina's idea that we start doing small things at the time, then we can sort of adapt these and create our own figures from things which inspire us.
Am I right to assume that someone who creates open educational materials is also open to questions by colleagues on the materials?
Of course.
Thank you.
The next presentation is talking about development of shareable activity library for geoenvironmental engineering education, and perhaps you can sort of introduce yourselves when you sort of start your presentation.
Yes. Okay. Good afternoon, everybody. My name is Gretchen Bohnhoff, and I'm at the Milwaukee School of Engineering in the United States, and along with my colleague here, Kristen Sample-Lord at Villanova University, we're going to be talking about developing a shareable activity library with geoenvironmental engineering applications. So in order to attract the best and the brightest students, we need to show that geotechnical engineering is challenging, interesting, and relevant. And so one of the ways that we can do that is by using active learning. Active learning has been shown to increase student engagement, performance, and retention. However, the time that's required to create these activities can often be prohibitive, especially for new faculty that are trying to juggle teaching, a new research program, etc. So one of the ways that we can help is by creating these shareable resources that are easy to implement in the classroom and ready to go. So what is active learning? There are a lot of definitions out there. Most of them are very similar. One that I like from the Berkeley Center for Teaching and Learning is any instructional method that engages students in the learning process beyond listening and passive note-taking. Active learning oftentimes includes groups. It provides the opportunities for students to interact with each other, with their classmates, and to learn problem-solving techniques and participate on teams. It oftentimes gives them the opportunity to connect the course material with real-world infrastructure. And one of the types of active learning that we are creating in this library is experiential learning. So what is experiential learning? Here's a modified diagram of the experiential learning cycle. So what experiential learning is learning by doing and reflection. So this is a type of active learning where students learn the fundamental concepts through doing and observation. One of the nice parts is that detailed prior knowledge on a concept is not required. So this is a hands-on form, see it, do it, learn it model. And so what we start with is adventure or challenge, which is crafted by the instructor. And then students participate in this adventure or challenge through active experimentation. Then after that, they go through a guided observation reflection, where it helps them determine abstract thinking, where they're concluding and learning from their experience. You can continue to go through this cycle as many times as you have time for a given activity. And in the end, you bring this to real-life applications. You relate these experiences to examples. So we are creating an activity library with geoenvironmental engineering activities, something that's going to be shareable and easy to implement in your courses. It's part of a larger NSF grant, so it's supported by the National Science Foundation in the United States. Previously, Kristen and I have created a geotechnical engineering activity library with geotechnical engineering topics. So this is geoenvironmental, and you can find that on the USugar website. There are a variety of teaching resources that are available right now in geotechnical engineering and geosciences. For a full list of some of these resources, you should refer to our paper. But some of these here, one is USugar, which is the United States Universities Council on Geotechnical Education and Research. There are a variety of teaching aids that are on that page, and many of them were created through special projects grants. In addition, CERC, which has origins in the geoscience community, but they've expanded out to include STEM disciplines. they have an extensive collection of pedagogical resources. One of the great things about the CERC resources, as Marina was talking about, is that they're peer-reviewed. And so they have an extensive rubric that they use to review these activities, and they can be rated through one of 4 levels. Those that don't meet the criteria are not published. So you know that those that are published meet those criteria. And then lastly, ISS MGE and TC306 has a variety of resources on their website. The proceedings from this conference, I believe we can find there now. In addition, you can find recorded webinars, virtual university, case studies, the John Berlin lecture from previous GEE conferences. So there are a variety of resources that are available for geotechnical engineering, but there's more limited for geoenvironmental engineering. And so that leads to our activity library.
Thank you, Gretchen. And so I'll be describing the activity library that we're working on in a little more detail and give you one very specific example for a taste. In addition to being a useful resource to engineering educators and enhancing student learning, we have some other goals for the library under development. And one is that the activities are as easy as possible to implement immediately for faculty, and they're very adaptable. So for that reason, the library includes activities that are for a range of durations, they're for different small group sizes, and they're in a variety of formats. There are several geoenvironmental engineering topics that will be covered in the completed library. They're listed in the paper. For today, I'm just going to show you a quick example of an activity that's in the fluid flow and transport area. So let's get to the fun part. Let's talk about one very specific example activity. This is an experiential learning activity, like Gretchen just described, where you do not teach the students anything at all beforehand, nothing, which makes it very adaptable to all age groups. There are pictures here shown on the top left. This activity has been done as a 60-minute version for university students in a soil mechanics class. It's been the same activity for a 45-minute version for high school students ages 15 to 17, and then also the same activity as a 20-minute version for children ages 11 to 13. It's just how many times you go around the wheel of the experiential learning cycle. The big picture takeaways from this activity are appreciating soils and geosynthetics as engineering materials, and that often in engineering, you're trying to achieve multiple and often competing design criteria. There are learning objectives provided in the instructor materials, but they're really for the instructor. You would not present these to the students first. You could talk about them after if you want. But the goal is they just try things, they observe, and then afterward you discuss why did that happen, and that can lead into the discussion of the technical content. So what does this activity look like? Again, everything is in Word files that you can adapt to your own classrooms, but what would happen is students walk in a small group, they have a table with a handout shown on the left and mystery materials on the right. It's very important that materials are only called geomaterials. You cannot tell them what they are. We can tell from the labels, these are sands, fine sand, usually a coarser sand like a medium sand, a bentonite clay, some gravels in there, some geotextiles in there. Those are geomaterials, but the students don't know maybe at this point what they are depending on their level. And from the handout, they're given these goals. This is a competitive activity. They're competing against other groups, and by a certain time point, they have to submit their final design. And their goal is that they will get a few attempts to design a system that lets water flow fast enough through their layered system to reach a minimum flow rate, which I'll describe in a minute, but also slow enough that it filters dirty water you're pouring in and cleans it. So somewhat of a competition in goals. The dirty water is just fines mixed with tap water, and the instructor materials, we tell you how to pre-prepare that. They have these geomaterials. They can use them in any way they want. So you'll see in the pan, that is just a soda bottle where we've cut off the top, put perforations on the bottom, and they'll fill up that soda bottle with whatever materials they want. Could be all of them, could be one. Usually the students that do all bentonite don't do well in this activity. And they'll fill it up, and when they're ready to test their design, they let the instructor know. So I'm going to skip ahead well, actually, I'll stay here. The top right picture is an example of testing. So let me go back. That plastic bottle, when it's filled up with layers, will go on top of the graduated cylinder, where the top half of the bottle helps hold it. And the instructor, like in the top right, will pour in the dirty water, and the students start to time it. To not be disqualified to meet the minimum flow rate criteria, the filtered water has to reach the 20 milliliter mark by 5 minutes. If it doesn't hit that mark by 5 minutes, they can't use that design. But if it does, now the competition is who can clean the water the best. So an example on the left here, these are two groups where they both met the flow rate criteria, but clearly the one on the bottom right had much cleaner water and won the competition. This was actually middle schoolers. They've done better than some of the college students. When it's the time point for the competition, like a competitive baking show, you have to run forward, put your final cake on there, and have it judged. They pour the water in all at the same time. Everybody's very excited, and we see who wins. And then there's usually a lot of curiosity about why did that one win? And now we discuss the technical concepts. So sorry if I went over time. We're working on the activities. It'll be available in 2027. Assessment and feedback is what we're trying to figure out now. Stay tuned.
Thank you. Are there any quick questions or reflections?
Thank you very much for your work. I have a curiosity. What are the standards for the review? I mean, what are the reviewers looking at for this material that is shared in this website? Because peer review in research is quite clear, I would say. But for this material, maybe it is not so much. So what is your experience?
We're trying to figure it out. We need to work with Marina because we actually aren't sure how to review these. And in fact, we were just talking, should it be geotechs? Should it be geotech and someone with expertise in education? We're not really sure. So right now we just ask colleagues who are willing to look at it.
And if you look at the CERC website, they have a pretty extensive process for their review. So we'll probably take a look at that and get started with something that's already existing too.
The next presentation is an educational case study, and it is basically discussing this big gap we have is that our textbooks are full of these unknown soils and these perfect graphs, etc. And we all teach some sort of settlement calculations to our students, but how often do we actually show how bad we are at that when we're comparing to measurements? So, so such case studies are extremely valuable.
Good afternoon. My talk is about a case study we prepared specifically for education. It has to do with calculation of settlements of a motorway embankment, but most significantly about the comparison between the computed values and the field measurement from a 2-year-long monitoring period. Let me tell you a short story of how we came up with that idea. It was back in 2019 when the geotechnical design of the embankments of an interchange was assigned to Εδαφομηχανική, the consulting company I'm working with. So back then I was calculating settlement of embankment of more than 1 meter. I shared my concern with Professor Marina Pantazidou, my co-author, and then 2 years later I called Marina again and told her that not only we have calculated such big settlement values, but we have also measured this on site. I will present shortly the components of our publication containing the paper and the online supplement. The combination of these two provides sufficient data so that it can be used for an education case study. Some things about the project area. It is located, the interchange is located at central Greece. It is at the delta plain of river Spercheios, located about 10 kilometers away from the shoreline of the Malian Gulf, but most significantly, it is close to Thermopylae, the place known for the battle between the ancient Greeks and the Persians. Here is the project area in a closer view. And let's move from the general view of the project to the design phase, focusing on some key features. The interchange has 1.5 kilometer length. The maximum embankment of the maximum height of the embankments is 14.2 meters. The embankments are founded on compressible materials, and for these reasons, the embankments are constructed in stages. Some of the embankments have been constructed reinforced with geogrids, and for all the above reasons, we decided that monitoring of these embankments is very crucial. The geology at the project area includes soft alluvial deposits. For the determination of the soil stratigraphy, 52 boreholes were evaluated. Here's the geotechnical longitudinal section of the main branch of the interchange, depicting the soil heterogeneity, which characterizes the area. You can see that the soil layers has different thickness between successive cross-sections of the road. Here is the characteristic cross-section we selected to present in detail in the current education case study. You can see here the soil layers, consisting mainly silts and clays, some interlayers of sand and gravels, and the geotechnical parameters used for the calculations of the settlements. Here you can see, I hope you can see, because of the size, the settlements we have calculated for each construction stage, and you can see here the contribution of each layer in terms of consolidation settlements separately. This table tells us two things: that the immediate settlement is only a small part of the total settlement, and that the contribution of the surface layer in terms of consolidation settlement is predominant. Let's compare now the values we have calculated with the one we have measured. You can see here the total settlements for each construction stage compared with the measured settlements from the settlement gauges. For all cases, the calculated settlements were greater than the measured ones. The comparison is depicted here in terms of time. Two main conclusions here we can make. For each construction stage, the measured settlements were stabilized. This fact, and also the fact that the measured settlements did not exceed the calculated ones, made us feel safe to proceed to the next construction stage. And the other conclusion is that the discrepancies between the measured and the calculated values is more pronounced at early construction stages, whereas this trend decreases as we proceed to the final construction stage. I will show you some photos from Google Earth during the construction. This is the area of the interchange at the start of the construction. Then, at the area of the selected cross-section when the first construction stage was completed. When all of the construction stages were completed. During the construction of the pavement at the area of this section. And finally, when the embankments of the interchange were completed. Now, two more closer photos. This is the final situation. At the area of the examined cross-sections, the embankments are reinforced with geogrids, with gabions at the slope faces. Here's another photo. And now we will move on to the conclusions. Why are the calculated settlements so different with the measured values? I will not refer to the most obvious reasons which have to do with the calculation method or the assumptions regarding the soil profile and the soil parameters, but I will emphasize the three-dimensional effects. When we calculated the settlements, we assume that the embankment is of infinite length. This is not the case, and certainly this is not the case at early construction stages because of restrictions at the construction site, which have to do with the construction sequence, the timetable of the project, and all this. And in this case of the interchange, the embankments are not infinite because the interchange is interrupted by three overpasses. One crossing over a railroad and two others above motorways. I will close my presentation. I would like to thank the contractor of the project, Terna SA, for permitting us to publish the material. I would also like to thank Mr. Ritsos and Dr. Kollios from Edafomechaniki for their contribution during the preparation of the project report. And I would also like to thank them and Professor Achilles Papadimitriou for discussing the discrepancy between the measured and the calculated values. Thank you very much for your attention.
Thank you again for excellent timekeeping. I'm sure that there are some questions or comments now. Well, I have a comment. Are you still measuring? Or where the measurement stopped?
No, the measurement stopped after a 2.5 year long period, and now the motorway is in operation, so it's rather difficult to keep.
keep measuring. I can appreciate, but where I come from, with creep settlements are a big issue, so we don't use stage construction for that reason. That it just triggers something which can be as big as a consolidation settlement. So that's one point. And the other thing, in my experience, why we over-predict settlements is that sample disturbance, that we are basically always underestimating the pre-consolidation pressure because,
yes,
I mean, especially when you have such a layered...
yes.
Layered
it's
deposit.
also the pre-consolidation stress, yes.
Yeah. Any other comments? If not, then we will move on. Thank you very much again.
Thank you.
The next presentation is addressing this very important topic which has been touched upon many times already today, developing concept inventories for geotechnical engineering.
Yeah, thank you very much, ladies and gentlemen. Welcome to my talk, which I present on behalf of my co-authors Wolfgang Fellin from Austria and René Sonnenberg from Germany. The talk was already advertised this morning, so thank you very much to Jennifer Case. If you're watching the video, take a look at the keynote lecture from this morning. I would like to present our findings and yes, the status of developing concept inventories for geotechnical engineering. A couple of months or years ago, maybe, we stumbled across the question, what would be the core skills that we need to teach our students in undergraduate courses of civil engineering? So we're not focusing on geotechnical professionals, but we thought, maybe in other words, what would every civil engineering graduate need to know if you wake them up at 2 o'clock at night and ask them, okay, can you explain active and passive earth pressure? Would they need to know that or not? And the second question was, how can we measure that? So how can we assess whether they achieved these competencies or not? We didn't think about this all on our own, but within an informal teaching network that myself and other colleagues, namely Katharina Kluge and another colleague from Cologne, founded in 2022. We regularly meet informally to discuss teaching methods, exchange ideas, and also material, and stimulate our teaching activities as a whole. And the answers to the question that I posed in the beginning, what are the most important skills, is not easy to answer. We took a look at the literature. John Atkinson published quite a few papers on that, and each and every one of us will have shaped his or her opinion throughout the careers. The practical experiences have an influence, also academic experience with our students, and also professional bodies and accreditation boards shape our opinion. So what we did is we put together roughly 120 statements, discussed them over and over again, and finally came up with 6 statements, competencies that civil engineering graduates should acquire during their studies. I don't want to read them out, you find them in the paper. Just to give you one example, we claim that civil engineering graduates with a first degree will be able to explain the differences between active, passive and earth pressure at rest and determine the distribution for a given soil profile. That was the start, and then we thought, okay, how can we measure and assess whether they achieved these competencies, and we carried on by developing test questions, multiple choice questions, in order to assess these competencies. Once again, we discussed over 50 test questions, narrowed them down and fit them to our core statements. And we applied them in a small field study, so to say, over the last couple of months in a peer instruction setting. I hope and I guess that most of you are familiar with that. It is that you pose the question in the lecture hall and you give a certain amount of time for the students to answer those questions on their own, first of all. This is the first round. We gave them 1.5 minutes, and then they're given a second chance to answer the question after having discussed with their peers and maybe change their answer and come up with another solution. Not all of our members of the network that I mentioned before took place in this study, but across 6 universities and 8 courses we tested these questions in the last winter term, mainly in soil mechanics courses in the 2nd year. And what I present and what you find in the paper is the total number of correct answers per round and also the changes in correct answers. I want to highlight this with an example. You already saw 2 of the questions before. This is another one on earth pressure distribution on a retaining wall with a soil profile with groundwater. The question is, what is the active earth pressure distribution resulting from these soil conditions and the groundwater? You have 5 possible answers. And we gathered, after each and every one of us had conducted the study, we gathered the answers. Let me see if it works. This is the number of answers that were given over all the 6 participating institutions, so 25 in total chose for option A, 1 for option B, and so on and so forth, by a total number of participants of 166. Please note that the number of answers is not necessarily the number of participants, because those were multiple choice questions. Don't ask me why somebody would opt for 2 of them, but this is how we evaluated it. And we then present the percentage of correct answers, that is 102 divided by 166, so 61% chose option D, and you see also the other ones. Maybe not surprisingly, this is also the correct answer, so this is something that we then evaluated further on, and we took a look how many students answered correctly in the first round. So in this case it was 49%, and after having discussed in the classroom, this number went up to 61. I don't want to read out all the numbers for all of the 10 questions. You find them in the publication, of course, but maybe some comments on how this worked. We found out that the replies to some of the questions were rather scattered, so at some universities the questions worked well, also in terms of understanding what we really wanted to test. Some terms were misunderstood, obviously, so the term stiffness, we also had a lot of discussion afterwards what is really meant by this term, and students were confused by the concepts of force and stress. And for these questions that I showed you before, you see here the results from the, in this case, 5 participating institutions. replies and correct answers in percentage for round 1, round 2, and then the difference. You can see here that in most cases the numbers went up, which is a good sign that discussion among the peers worked. In some, it also went down. And this gives you then a possibility to discuss the reasons why or what went wrong, so to say. Another remark, some of the numbers are highlighted in green because in the literature on peer instruction you find that a percentage between 30 and 80% in the first round is a good starting point for peer instruction. If the numbers are lower, the question is too difficult. If they're higher, the question is too easy, and this gives us opportunity to further work these questions out. And the title of the paper is Developing Concept Inventory. So this was intended to be a first step towards further promoting this idea of developing questions that really test the understanding of the students. So an assessment of the teaching process rather than individual students' performance, so to say. And I remember that Jennifer Case, she asked the question, which of the questions was better suited? This is something which we need to work out further in order to make it real concept inventory questions which try to assess the students' knowledge of these fundamental concepts, which can then also be used to provide some formative assessment of the teaching. And yes, there are some hints in the literature. What is missing, for example, are student interviews in order to check whether these misconceptions that they have are really covered all, or if something is missing, if we use the correct wording. So there is all kinds of pitfalls and biases that we need to avoid. We would like to invite you very much to provide feedback on these questions and help us to develop them further, and maybe at another occasion we can then present how it went on. Thank you very much.
Thank you very much. I think these sort of tools are exactly what is required in teaching. Any comments?
The exercise on active pressure is very interesting. I would like to know the students that reply to that exercise, how many disciplines on soil mechanics did they have? So at the moment of this test.
It depends. It's a good question. It's usually in the third semester, so second year of civil engineering curricula. And it is, or we post the questions usually 1 or 2 weeks after the topic had been presented in class. So it's not 5 minutes later or half an hour later, but we gave a bit of time to process the information, and then we
But
post
this topic is treated in the first discipline on soil mechanics?
Yes.
A semester's discipline?
Yes. It's the soil mechanics course usually towards the end of the course.
The end of the course.
In most cases. Some of them have them 1 semester later, but it's the second year basically.
Okay, thank you.
Okay, I think given the time constraints. Okay, very quick one, if you promise to be quick.
You're very welcome to get in touch with me and my colleagues later on, of course.
Thank you. Thank you for your presentation. It was very interesting. If I understood well, you use your questions to check understanding and knowledge. Yeah. One of the and within that context, that should be it. What I would say is, I've seen in what you call peer instruction, some students convincing their colleagues of wrong answers. And you need to make sure you address that in your process. So have you done some sort of final discussion to address those misconceptions and to address those wrong influences, if I may say so?
Yes, good question. I cannot talk for all of my colleagues, obviously, but I mean, this is the point. It becomes obvious when the numbers go down, because then you have a strong motivation to clarify things. We also went or observed the audience a bit during the answering process. You know, you hear a lot, and maybe you can address this later on. This is obviously very important to do so, yes.
Okay, so let me just make one last suggestion, and maybe linking to Marina's talk. We may need some sort of guided process for people to use the questions, but at the end, introduce some discussion sessions.
Yes.
Yeah, thank you.
Thank you very much. Very sort of good suggestion. The next presentation is going through this maze of geotechnical books, and it is very interesting comparison on what they contain, as we already discussed that compaction is not in all of them.
Thank you very much, Mina, for the presentation. So I'm moving quickly into the presentation. I was dealing with how university textbooks worldwide are dealing with soil mechanic core concepts. So the aim of the study is to explore how these soil mechanic core concepts are treated by looking at table of contents of the textbooks themselves. So therefore, there are some assumptions here. And the first one is that textbooks are one important teaching material, reference material in a given course, because they're often authored by instructors with significant experience in teaching and research. The structure of textbooks is typically designed to introduce fundamental concepts in a logical sequence, therefore, basic concept before typically more advanced concepts, and then the table of contents of the textbooks can be informative, because it can be considered a sort of roadmap for what comes in the textbook itself. With this in mind, I guess I close everything with this in mind. Instead of clicking, no, that's back. Okay, with this in mind, 42 textbooks were analyzed. In the paper you will find a table for 24 that are written in English, another table for the 18 that are written in, maybe I skipped one. Yes, I just skipped the fact that, in order to compile this list, I asked many of you. I guess there you are also here, because I sent an email to TC306 members. I interacted with 22 of you, and then I got also information from personal knowledge and bibliographic review. 42 textbooks, 18 of which are not written in English, many languages, but of course, these cannot be considered at all a comprehensive list, doesn't have a statistical significance. It's many examples from which I drew some conclusions, and hopefully also it's a source of material for, for you, or for readers, textbooks currently available, maybe because some readers may find that books that they didn't know before are useful to them. It's a sort of reading list. Some others maybe can delve into the historical writings of educators from the past. For instance, Taylor 1948 is one of the first books, together with Lambe-Whitman. They treat things differently, and also if I think about Lambe-Whitman, they say explicitly this book is designed as an introductory course in soil mechanics, as a book for an introductory course in soil mechanics. So some of the authors explicitly, I would say most of the authors implicitly do it, all authors implicitly do it, but some say specifically what their books are for. For instance, Terzaghi and Peck, and even in the latest version with co-author Mesri, they say it's a book for both students, university students, and the practicing geotechnical engineers. Different sections suit to different audiences, and that can be done. If I go to more recent books written in English, I'm just picking two here because they are widely used from what I could see from the results of my non-statistical significant survey, but anyway, also because they have their two websites that are including significant amount of extra material that is, some of which is not for the students, it's also for the educators. It's also a marketing thing, I believe, but some of that is also interesting for the educators that want to use those books. In the books that are not written in English, I'm not going to mention anyone in particular. I just want to highlight some features, and then later on we'll see for the full set other of these features. I can say that all books devote at least one chapter to groundwater flow, to volumetric compressibility and consolidation, to almost all books to soil strength. And some books deal with continuum mechanics, concepts, or others. One thing that I wanted to at some point say is, you know, I've been talking about table of contents, no, maybe I'll say it here, of chapters. When you have a table of contents of a book, of course, you have chapters, sections, subsections, and you have a long list of titles to draw for. I just base my analysis on the chapters because I'm, well, one for convenience, I stopped at the chapter level, and the other is also for methodological coherence, and because authors, that when they write their books, they have to decide how to structure their books, think about how to subdivide the material, and the choice of making chapters that have a certain title and have a certain length, some of them have very long chapters, some of them are very small chapters, it's a methodological choice that, you know, reflects on what they want to say. This grouping is subjective. I did it, after looking at all this material, I grouped topics in 4 big classes. Introduction and basic characteristics of soils, soil investigation and testing, soil mechanics core concepts, and geotechnical applications. The chapters that belong to these different books, you can see how they are distributed, but I'm skipping in the paper, I'm skipping that part from the presentation today because the time is short. And also today, in the next few minutes only, I will concentrate on soil mechanic core concepts. Indeed, it was also the core of my, case study. The core of soil mechanics textbooks are the concepts that we can say also, it was mentioned today in different ways by Marina and others, characterize the discipline also from our keynote lecture in the morning. Many core concepts in geotechnical engineering are deeply interconnected. We know that. It's difficult maybe to draw clear lines separating specific topics. It's difficult to group concepts coherently in broader teams. I may even say that it's difficult to agree on terminology of what concepts, topics, themes are within our field. No? I'm saying among ourselves. Maybe for that same reason, exactly for that reason, it's difficult. I gave a try, and my take on this is this one. I decided that these could be 7 main soil mechanic themes that group the core concepts of soil mechanics: stresses and strains in soil, in situ stresses, groundwater flow, stress-strain relationship, volumetric compression, consolidation, and shear strength. Now, they come with associated terms, concepts, topics, so it's like this is not a word cloud, but almost, there are many terms that cluster around the main terms that I used here to define the themes. I just want to say briefly that, of course, this subdivision is also arbitrary. It's mine, I did it here. How did I end up doing what I ended up doing? For instance, Team A, continuum mechanics, stresses and strain in soils, and Team B, stresses distributions in the ground. They address sometimes similar things, but one concentrates more, in my opinion, when you deal with elementary volumes, you're thinking about stresses and strains in soils. When you are dealing with the ground surface, subsurface from a ground level, you are dealing with in situ stresses. When the water is moving, you go to the groundwater flow, but the water was already present in teams A and B. Stress-strain relationships, in principles, could be a broad theme encompassing all the modeling of elastic, elastoplastic, viscous, whatever, even time-dependent behavior or material. But in my opinion, it's good to give a specific, dignity of a theme to deformation due to shear stress. It's different from deformations and due to volumetric, different from volumetric compression and swelling, and also the consolidation that really brings a very foundational concept of geotechnical engineering, the time-dependent deformations that are there because of the dissipation of excess pore pressures is also there as a theme and as a dignity of being a theme, and shear strength, soil failure, that is not only the final part of the behavior of material, but as, a meaning in itself. With that, I say that, you know, there are most of the books covering themes A, B, C, also the final ones, maybe not specific chapters, not for all books for the theme D. And I'm skipping for time reasons these that you can find in the paper, that is how the different books indeed put these concepts in a sequence in their own table of contents. I'm skipping these because I want to give you some examples, specific examples. If I go to Craig soil mechanics, you can see they are highlighted the 4 chapters that are dealing with the soil mechanic core concepts. And if I go here, indeed, everything starts from seepage, therefore groundwater flow, then moves to the top part, effective stresses, and then consolidation, and the final chapter, shear. So, few chapters, few titles. I'm not saying that all the rest is not dealt with necessarily in the book, but you know, it's not there highlighted by means of chapter titles. If I go to DAS, more chapters and a different, I don't know, flowgram, how you want to call it, I don't know, starting from the same position, that is groundwater flow. If I go to the Elements of Soil Mechanics 10th edition by Smith, same starting point and different ways of moving by means of a relatively small number of chapters. Here, the author decided also to put parts 1, 2, and 3 in their Soil Mechanics and Geotechnical Engineering textbook. In Italy, for instance, Berardi starts from stresses and strains in soils in general before moving to water and then moving down to consolidation and the rest. And Lancellotta in his English book also starts from the top, but you can see the titles of the first 3 chapters. Continuum mechanics, basic constitutive models, the porous medium before going to the rest. That is essentially everything else, stress-strain relationships, and then groundwater flow only at the end. Matheus Fernandes here in its very last edition of volume 1 of Soil Mechanics in Portuguese. This is the flowgram that I see from this book, at least looking at chapters. And I want to highlight the final one that is a little different from the others, because at least looking at how the chapters are titled, although there is a lot more detail in the table of contents, shear strength is there from the beginning. And it's not many books do that, and it's also there at the end. So at the beginning, at the end, triaxial stress or behavior, and in between there is the rest. A few of the books that you will find in the paper are specific points of view by definition, because when Moorwood writes a one-dimensional introduction to soil mechanics, that's the take, or Briot saying, I am dealing with unsaturated soil mechanics from the start and not only as a final chapter. Wesley dealing with sedimentary and residual soils, and some others with a specific take on critical state soil mechanics. Finally, to conclude, I tried to identify commonalities and divergences in topic coverage and sequence in many introductory soil mechanics and geotechnical engineering textbooks. Hopefully, this can be a reading or can be used by different geotechnical educators. And I'm pretty sure that if you read the paper, if you look at the paper, if you also only see the table, for instance, you may focus your attention on different findings or different things depending on what you are looking for at the specific moment of your whatever, career or interest. So maybe some of you may be interested in landmark books or intriguing sequences of topics or new references to explore. If, it would be successful if some of you find this good food for thought, and maybe possibly some of you may say, okay, the list of textbooks is the most important thing. I see it, I know that they are there, I click and I just check what they say. Thank you.
Very big challenge of finding a textbook which will teach what you want to teach in the country you are in. I really got shocked when I moved from UK to Sweden, and I realized that people are not able to read these long English texts, so that was restricting my choice of books.
If I may use your comment as a question, if I may.
Yeah.
No, indeed, all of us as educators, we are striving to find, if we are not textbook authors, because if we are authors, we do what we do. But then indeed, it's important to give references to the specific, explicit reference to our students, and depending on where you are, really the culture drives what people want.
Yeah, yeah. Any other comments or?
Okay, so I don't use a textbook. I think none of them are, right. So, yeah. So I mean, I have notes, but I think you need to, as a teacher, you need to integrate the applications, and as you're doing it, right, you can't just get students to read the textbook. But so what I do, I give them a long list of textbooks, which are on your list there, and say, when you get stuck, there's an infinite number of these books. Find one that works for you, because they're all written in quite different styles, and they appeal to different students and maybe different instructors as well.
So,
right?
so when you say works for you, you mean the student or you mean the teacher? Because Marina was clear this morning, and I agree, or this afternoon, when she said, there is resources for the teacher and resources for the students, and a textbook in itself is not necessarily for both. Okay, conversation closed.
Okay, I think in a way this was a very good sort of lead on to the next presentation, which is now looking at things from the student's perspective.
Thank you very much. So here we see an example of collecting student preferences, not because, as Marina said, it's our way of judging our work, but to stimulate some thought. So we know that since the 90s, slide sharing presentation have progressively replaced traditional chalk and talk lectures, and the effectiveness of slideware lectures have been debated for years about the content, about the structure of the slide, the style, and so on. Now we know that to maximize efficiency, presentation should leverage two channels, the verbal channel, so the text and the narration of the speaker, and the non-verbal channel, so images and animation. The objective of this study is to investigate the preferences of the students and teacher concerning stylistic aspect of the single slide, so not the lectures, but a single topic. We selected two key topics in geomechanics, shear strength in drain condition and drained and drain behavior of soil during shearing. And for each topic, we prepared two types of slides. One, we call it textbook-like style. We call it like this because there is, let's say, a long text that is explaining the figure, like is usually done in a textbook, as we saw a minute ago. And the other one is a presentation-style slide, where there isn't this long text explaining the figure, but the figure is designed in a way that it should explain itself, let's say. Just to give you an example, this is the slide for the topic of shear strength, the textbook-like slide. So I don't comment it, but as you can see, there is a long text, and this text is explaining what you see in the figures. The figures are showing the shear stress as a function of the shear strain and volumetric strain with shear strain or the void ratio. The same topic, but considering the presentation like style, we only have the graphs with no text because the teacher is assumed to explain during the lesson this graph, but there is an introduction of main quantities that are recalled in the slide. For the drained and drain condition, again, there is a long text that is explaining, basically giving the definition of drain condition and undrained condition, and then a graph that is showing what is happening with shear strain if you run a drain test, so if with compression or expansion, depending on the type of soil, and the change in excess pore water pressure if you are running an undrained test. The long test, so these two graphs are identical to the previous slide, but the long text is replaced with a figure. Okay, so we showed to the student these two slides, and we asked them, which slide do you prefer? Do you prefer in the sense which one you prefer to have it during the lesson as an handout also for studying afterwards? And then why they want this slide, and they need to write a short text motivating their answer. We collected the answers using a book lab, and then we elaborated the result. We surveyed 80 students, about 80 students. 40% of them were master students during the, we call it graduate student because they are at the master, usually at the, what is 4th or 5th year of civil engineering or water and geological risk engineering. 60% are bachelor students in the 3rd year of civil engineering. In both cases, the slides were shown during a lesson dedicated to a recap of the topic, meaning that these students learned this topic before with totally different slides. So the teacher showed these 2 lessons, asking them to recall the main concept of the topic before moving to something else. And the answers were collected during the 1st semester of this year at the University of Padova. These are the answers for the student. So regarding shear strength, most of the students preferred the textbook-like style, most of the undergraduate students, while for graduate students, they were divided half and half. For the drained and drain condition, there was a slight preference for the presentation-like style for the undergraduate student, and a clear preference for the textbook-like style for graduate student. People who said that they prefer a textbook-like style, they wrote that they prefer this slide because more writing help them to better clarify and comprehend the topic, and it is more useful for at-home study. Who preferred the presentation-like style, in most of the cases, said that less writing is useful to have in-class engagement and active learning, maybe ask questions, because they are forced to listen what the teacher is saying. They prefer colorful and intuitive graphic, and they think that less graphic help them to understand, maybe because they are not distracted to read the test. So clearly there is a disagreement between the preferences of undergraduate and graduate students, maybe because of the different academic level and also the ability to take notes or their visual literacy. And, but overall, there seems to be a slightly higher preference for textbook-like style. And now this opens a question, why don't they buy books? What we, I mean, no, this is a serious question because we saw the work by Michele reviewing all different types of books, but what we observed across all different disciplines is that compared to the past, students don't buy books and they study on their own notes or handouts. So at this point, I clearly understand why they prefer the one with more text, because that is their textbook at the end. Of course, with this survey, there are a lot of biases that are difficult to take into account, like cultural teaching, differences in learning preferences, if they have the book or read the book at home, and so on. Then we asked exactly the same question to 21 Italian teachers of different age. We contacted them by email and asking them to compile a Google form. So now again, we show them the 2 slides, asking which one they prefer for their classes and why. And this survey was done in January 2025. Now the answer is clear. They clearly prefer the presentation-like style, clearly. And the reason is that they believe that less writing helps engagement of the student in class, and it is more clear, and maybe the graph is more colorful and intuitive. So they clearly prefer the presentation styles liked because they prioritize in-class engagement, which is certainly good. But this is in contrast with student preferences, maybe because of different visual literacy between student and
teacher, or maybe because of different objectives, because while the students want to have material to study at home, the teacher want to increase in class engagement. We have to think about that. Of course, this study has several limitations, cultural biases. Of course, the result might change next year with a different cohort of students. And we couldn't analyze the performances of the student because we all know that what they prefer maybe is not the best for their learning. We couldn't check this. And sample is significant but could be increased. So it is clear that while teachers prioritizing class engagement, student preference reflect their need to have both in-class engagement, but also material for an independent study. So it is a challenge for us, for the teacher, to balance these two aspects. So it is challenging to find a balance between written text, graphic, images, narration, so without being, let's say, too concise in the text, as the teacher would prefer, but also to not to be too verbose as the student might desire. So this open for some question and for thought, let's say. Thank you.
I'm sure that there will be some comments.
Thank you very much for your presentation. I teach a foundation design course, which is the product of geotechnical engineering, and students always complain about the amount of astronomical correlations in the course. So how, like, what's the recipe? That's foundation design, it's about lots of correlations, and it's unlike concrete design, things are not very clear and you have to make assumptions, and there's no really a magic recipe to make it more appealing to them. So I don't know, what's your thought about that? Thank you.
Yeah, so you are talking about like the design of a presentation or of a lecture for a specific topic like this, like correlation for a foundation. Wow, that's an interesting question. Yes, there is a lot. There is a lot. I don't have an answer for that, but I clearly understand your difficulty in this, and we're facing like every day. Finding a balance is extremely difficult because when the point is that we want to highlight here is that when we are happy with the material, we think we found a balance. Maybe for the students, is not.
Yeah, I think that reflects on which is the good textbook, for the students or for the instructor.
Yes.
Thank you.
It's the same point, yes.
Thank you very much.
Thank you very much. What a very interesting study, and I think you sort of pointing us towards more questions, the teacher and student perspective. And I suppose what I'm really grappling with is, under what conditions would students buy a textbook these days? And I think many of us are living in a bit of a fantasy world, which is our own memories. I mean, obviously the one thing is about the cost of higher education. I do think that some instructors, certainly my understanding in the US, assign homework that you need the key from the publisher, and I think that's a model the publishers are using. But like, what is the future of textbook is even my question. And you know, the colleague in the front who said he writes notes. So I remember a time teaching where I felt it was so important that students used the textbook. You know, and I would like insist, I'd find the right textbook and insist that you had it and set things from the textbook. And I would sort of look down at some colleagues who would write these notes. I always think, you can never do notes that are as good as a textbook. I now am entirely agnostic about that previous, you know, that feeling I had at the time. Because I think things have changed very, very fast. So I think your question of The one is, why would they buy a textbook? And the other thing is, what do they think is the purpose of slides? And I'm really fascinated by what you've come up with. It does intersect weirdly, awkwardly with the question on open education resources, and I appreciate the chair's comments. You know, how many of us are checking the copyright on every single thing we use for every single thing in our classroom? I think that's another intriguing question, and of course AI just ignores all the copyrights. So, at any rate, thank you. You just got my head buzzing with more questions. It wasn't a question, that was a comment.
No, it's an interesting point, but I think I have a small answer that our university at the library, we targeted the question, maybe the book costs too much for the student. So we did online, the library buy online book, so all the students have free access to the online version of the book, and still they don't, so it's not the cost the problem. There must be something else.
That's very interesting.
Thank you. I remember this morning one of the presentations reported an opinion of a student that said that he enjoyed when the teacher explained matters in the board. Okay, my opinion is that most teachers include too much information in the slides. The slides, in my opinion, should just serve to put the graphs and the photos, the figures, and all the explanation should be done by the teacher. In your last sentence, you write that students probably desire more verbose from the teachers. So I congratulate you by the excellent presentation and by this extremely interesting case, but I would disagree with your last conclusion, because if we are convinced that students desire simpler slides and more words from the teacher, is that we should do, because we should serve the students and their preferences.
Well, I have a very short comment on that one. I think part of the thing is that if I'm thinking about my courses, only 50% of the students are in the lectures because they have jobs on site, they have children to pick up from a nursery, etc. And the university teaching hours don't take this family life into equation. So I think there are reasons why students want to have more text, because they can't be present in all lectures because of family reasons. And especially now with this living cost increasing, more and more are working on the side. Somebody else wanted to comment as well.
That was precisely my comment. So I wonder if the students prefer more text because they are not present, or they are not very present, or not physically or mentally. And then they say, okay, it's time to study. So they go on.
But consider that this survey was done in class. So the people that answer were present in the class, right? Maybe, so most of them were surely people present every day, but still it seems that, I don't know, time to think about it. I don't have an answer for everything, but just...
Yeah. But then I also maybe sort of think there is a very, very big risk of it teaching notes. So I came to Sweden, and now we have hundreds of graduates who think what my predecessor invented: consolidation theory, settlement calculations. I mean, this guy is amazing because the whole soil mechanics in his notes doesn't have any reference to any of the original sources. So it is very dangerous for notes which don't have these origins.
Thanks.